Théo will from Imperial to tell us about spinning CFT correlators which are ADS twistors, please.
For the organizers. So yeah, I'll tell you about how to get these CFT correlators from Twistor space, and hopefully convince you. So first, let's start with amplitudes before correlators. So I don't have to convince most of you that final diagrams, they're long, they're hard to compute, and most of us wants to replace them. With more like this point of view is a more on-shell point of view. And to explain this sort of hidden simplicity, Witten published his groundbreaking paper where he showed that in Twistor space, amplitudes localize on simple curves. And that explained that sort of miraculous simplicity. And following that, people then took that idea further and constructed the Grassmannian and then the amplitude and all these things. It all comes from this point of view. And the aim of the talk is to show you how to start doing the same thing, but for correlators. So now people are very interested in cosmological correlators or just in ADS in general. And if you thought that Feynman diagrams were hard, Witten diagrams are even much harder. So we need something even better. But we have conformal symmetry, which is extremely constraining. Problem is, even though it's really constraining, it's not straightforward to impose all this symmetry necessarily. And this is why there's been quite a lot of languages which you can express conformal symmetry. So from position space to embedding space, Mellin space, all these have their advantages on basically how to impose this. And so I'll tell you now how to do that in Twistor space. I'll also focus with on the more point of just conserved operators, which is the more relevant. So let me tell you first the summary of the talk. Kinematics will be automatic in Twistor space. And by kinematics, I simply mean conformal symmetry and conservation. And the dynamics will be a choice of basics in Twistor space, a choice of function, which I'll explain. So this whole program started with this paper here, and you can see lots of people got really excited with this idea, and I'll try to explain why it's exciting. So I'll mainly talk about the paper my supervisor and I wrote, which is the second one here, and tell you a bit more the Twistor point. Okay, so first I'll explain very quickly Twistor space, basically just the Penrose transform, the most basic level, and then tell you how to translate it to the Grassmannian. They're very, very closely related. It's just a Fourier transform. And then finally, I can tell you some of the advantages of this formulation. So the first obvious one will be that spin is very easy to incorporate, which is not something you see usually in position or momentum space. And then finally, I'll talk a bit more about what we actually did and some of the subtleties there is between the two. Okay, so this is Twistor space. So you have a double vibration. On the right side for you, you have position space written in spinor notation. And usually you just take the complexification and then impose a reality condition at the end. And on the left-hand side, you have Twistor space, which is nothing but a subset of CP3 with coordinate Z, which is what we call a twistor. Now, how do you relate positions of twistors? You just impose the so-called incidence relation. So you write down your coordinates with its mu lambda and impose this relation. And there you have it. So why is it interesting? The interesting part is that it's a nonlinear correspondence. By that, I mean non-local. So a point here corresponds to a sphere or a line, depends how you view a CP1 on Twistor space. And Inversely, a point in twistor space corresponds to a null-to plane in complexified space for geodesic in the. So now you know everything about the twistor geometry. What we want is to put fields. So how do we encode fields? We do that through the Penrose transform. So here's your space-time field. The way to do it is you pick some function of the twistors, and you have to integrate over CP1. So remember the lambdas part of this twistor, and they form a CP1s. You encode all the spin through these factors. But because it's a CP1 integral, you need the whole integrand to be scaleless. And because the whole integrand, including the measure, has to be scaleless, this imposes this homogeneity condition on the function you pick. And that restricts the allowed functions you can pick very much. Okay, so after all this, what do you get? You get a field that obeys this equation. And that looks like a simple enough equation. Why did we need this complicated integral for this? Well, you don't need it, but as you can see, as you'll see later, actually, it will simplify things a lot to just think in terms of this f rather than this vice. Okay, so the first thing to notice why it's so useful, this z, they transform as the fundamental of SL4C, which is just the conformal group. And so the generators of the conformal group are just linear and all on the same footing. What that means practically is that if you want to enforce conformal symmetry, you just need to consider dot products of this SL4C. So we'll restrict our function to just depend on this scalar, and that's it. Conformal symmetry is done. Now, I'll mainly focus on 3D. So we're working on the 4D generalization now. But for 3D, the conformal group is now SP4, and I'll call my twistors these lambdas, which are parameterized with this. And the same thing happens. The conformal group is again. Okay, so that was the first condition, make conformal symmetry manifest. Now let's move on to the second condition, conservation. So in position space, all you need to do is just hit the current with this operator. Twisted space, the derivative is very easy. You just have to use the chain rule. You can show that it's equivalent to this formula. Now what happens is that if you just hit that inside the Penrose transform, you're gonna get this. Remember, these are what contains the spin information. And automatically, you're gonna have to contract 2 pi's. These are just SL2 indices, and pi.pi is 0. And therefore, this is just 0 at the level of the integrand. And that's it. So conservation is automatic. Okay, so this is the ansatz. Here's a collator in position space, and we'll have n nested Penrose transform. And the point is you choose your function out of dot product of these twistors corresponding to each of these. And the game is then just to see what f should you pick. Now, I told you all these properties that are manifest, but I haven't told you if you can get all correlators in this way. 0 is conformally invariant and it's also conserved. So this is not obvious, but it turns out you can get all correlators. So briefly, at the Grassmannian, so since you only care about these variables, you can exchange them with theCij's, which are called the link variables, through just the Fourier transform. So that should be lambda I, lambda j. It's in 4D. It's just the same thing. And you call this A the Grassmannian. So you see, it's straightforward to go from one to the other, at least in principle. And from this A, you can recover the momentum correlator through this formula, which I'm not going to really explain, but you can do the same story I just told you from position space to twistor space by trivializing the conformal symmetries from the momentum point of view, and you arrive at this formula. Okay, so that's it. It's because you might see a lot of this paper written in the Grassmannian language. So just to tell you, the link is principle very easy.
I mean, sometimes when you work with massless fields in De Sitter or something, or even in ADS, the left-hand side can have large volume divergence. Show up on the right-hand side, or those are things which you cannot get from space.
Sorry, which divergence are you talking about?
Like, you're just working with the massless phi cube theory, or massless gravity, and getting a large volume, something from the radial integrals.
So
show up on the right.
Question of divergence, actually, I'm going to touch on that later on. Because indeed, like at the 2 points, this formula is a divergence and you need to take care of it. You can do it, but this is one of the differences between the Grassmannian. I'll touch that later, and if you still have questions. Okay, so now you did the hard part, which is what is the Laplace transform. So, as I said, all the spin information in these factors here. So if you want to go from the scalar to spin 1 or whatever, all you need to do is turn on these factors. And then because the whole integrand still needs to be to have homogeneity 0, you just have to compensate with the homogeneity of this formula. And at 3 points at least, this is very easy. It's just a question of adjusting the power of your answers. So as a direct consequence, I have the double copy. So here, this isn't the occasion to show you actual some examples. So just take the 3-point scalar. This is the representation in twistor space, just fraction. Now take Yang-Mills, where this is just with these 2 logs, related to the fact that you can get 0. So if you didn't have these logs, if you integrate, you get 0. But we found that if you regularize with these logs, you get perfectly the right answer. But the point is you get gravity just squaring Yang-Mills and dividing by the kernel, which is just a scalar up to these logs. But this is just a consequence of the fact that spin is very easy to handle. What is maybe surprising is that there is not a single option for spin 1, spin 1, spin 1 correlators. You could have phi cubed, for instance. But indeed, if you square Yang-Mills, you get gravity. If you square f cubed, you get phi cubed. So it seems it works at a physical level, which you might have not expected. So now I'll move on to the more some subtleties between the Grassmannian and the twistor space. So before I go on with twistor propaganda, at the end of the day, all you want is just whatever gives you the easiest answer. And so we compute that 2 point and 3 points, both are quite easy. They computed the Grassmannian at 4 points, and we haven't computed the twistor at 4 points. So for the 4 points, I don't know yet exactly if the twistor will be as simple as Grassmannian or not. But having said that, let me tell you some of the lessons we learned from 2 and 3 points. So the first worry from, it was Pimentel, the author of the paper, who noticed, was a bit worried about that, is the word identity. So the Grassmannian gives very naturally the homogeneous solutions to the word identity. Now, this is a little bit, it's not quite ideal because they managed to reconstruct the full correlators by knowing the discontinuity, but it's not a straightforward calculation. Whereas in twistors, It's straightforward. You grab the Yang-Mills I just showed you. You put that in the Panner transform. You do these integrals, and you're done. It seems these word identities, these non-homogeneous word identities, are linked to the presence of these logs. So actually, there's been recently, like in the last few weeks, a paper which addressed this issue in n equals 2 supersymmetry. They managed to address the Grassmannian with additional factors such that it gives automatically the non-homogeneous word identity. That they require supersymmetry, and it's a bit more involved. Here we didn't say anything about supersymmetry. So this is the first difference. So F cubed corresponds to the homogeneous solution, and Yang-Mills corresponds to the non-homogeneous solution to this word identity. And so for Yang-Mills, you actually need to work a bit harder. You can do it, but next thing we did is to give the bulk origin of these correlators. So to do that, we constructed the 2 points in the bulk ADS using the same method in the Twistor language, and then take the appropriate limit and see that we get back where we thought we should arrive to. So for that, we had to construct these points, which was actually very straightforward because it's literally the same logic. So another reason why this is interesting is that I showed you all these Twistor correspondence. It's really 4D. In 4D, you can show that the Panner transform gives rise to all the solutions. Now, since we show that they arise from a 4D perspective, it's just to give a bit more evidence as to why it makes sense that we get all correlators in 3D. It's not, I wouldn't say it's a proof, but it's just more evidence that it makes sense. Now, the third thing is about space-time signature. So the Witten transform, which is the formula that relates Twistor or Grassmannian to momentum space, is what we call the Witten transform. And when he invented that transform, he did it in split signature. He didn't do it because it's particularly unphysical. He did it because there everything is real and you can actually define this transform. And then he said, oh, someone should really find the correct transform in niches we care about. But it's been more than 20 years and no one, to my knowledge, has found it. So whenever you come from the momentum space route, you really are working in the split signature, which means that then you have to do some analytic continuation to get to the Lorentz answer that we all care about. And I'm told that doing these analytic continuations is not straightforward. Now in the Twistor space, you just start with complexified spacetime. Take the reality condition at the end. And that takes care also of another, it's not a problem, it's just nicer. In the reality condition from the start, you have to work with functions. These are just derivatives of delta functions. And the complexified case is just some rational functions dressed with these logs, as I showed you in the previous example. Just look very simple. There's no need to do not the Fourier transform of this thing to be able to calculate and then come back to Twistors. You can just do this contour integral. I mean, very straightforward. And the last thing we did is to come back to the 2 points. So as I mentioned, there was an issue of divergence. You can see clearly when you do the calculation that you get the right answer times infinity. But to cancel that infinity, you still need, I say, to cheat a little bit and take a contour, which is not something that came from the formalism itself. It's more something you impose to get the right answer. And so with Mariana, we thought, let's try to actually regularize this thing and see maybe Twistors can help with this case. And it did. So it was quite easy to regularize because you can go to Euclidean. You just get the finite answer. Now in these 2 points, we also wondered, so we're primarily interested in the conserved case, but how far can we push this formalism? Can we go to the non-conserved, i.e. Massive fields in the bulk? And to our surprise, we could. Why is surprise is because usually twistors are good with massless fields, right? So the fact that we get massive fields so easily, it was the first thing we guessed. Again, it's all to do with preserving this homogeneity and changing it and just adding whatever you could without introducing new variables. Well, it worked. At 3 points, I don't know. So I don't know if it's an accident of 2 points or not, but it's interesting that we could do this generalization. Other people also found this generalization. So that's it, really. The main point I want to remember is just twistor space makes conformal symmetry and conservation completely manifest. And spin is just taken care of. You can get all the correlators at least at 3 points. You can get, they got Yang-Mills at 4 points in the Grassmannian. Gravity still need to work a bit harder to get it. And then yeah, these are the small sort of subtleties between Grassmannian and twistor formulations, i.e. the word identity. Thank you.
Francis?
So to my question, my question is time integrals. Let's say if you were doing the computation, time integrals to compute the wave function. Divergences from those time integrals, even for let's say a 3-point function. Is that divergence located in place?
Well, I guess this is a bulk calculation, right? And the point of all this is forget about the bulk and reconstruct everything from the boundary. So I don't think there's a straightforward analog of taking this time integral here. So even if you get a divergence, I would know like if it corresponds to that same view, because here the point is really you stay on the boundary, if you will. I would, yeah.
Well, I have one question, I think. So you mentioned at some point some double copy algebra.
Yeah.
Right. Is that related to the, like, some people doing like homotopy algebra for double copy, semantic algebras? Is that related?
Well, I'd say in the grand scheme of things, probably, but
Right.
this is a far.
Yeah.
I mean, they're still like it's at the level of amplitudes. I don't know. Well, I don't think there's been any work on this homotopy algebra level of correlators.
Okay, sure.
So I'll stretch to say that for sure it is related, but probably
it's a hint.
Yeah, this double copy is pretty hard to do in position space or momentum space. I don't know how to do it, but
It's just squaring of the Young-Wilson. At least for 3 points, it's just squaring.